All right, so hello. Today we are going to start talking about thermochemistry. And so here we go. So we're talking about thermochemistry. What we're really talking about is how energy is transferred. And it's really just a discussion of energy and energy transference. And so the first thing that we want to talk about is thermodynamics. So thermodynamics, wow, sorry I missed the line a little bit there, is the study of energy and its transformation. What we care about is thermochemistry. And thermochemistry is the study of chemical reactions and energy changes associated with that. And so that's where we're starting. We're going to start jumping right into the nature of chemical energy and how that works. So there's going to be a lot of information here that's fairly complicated, but we're not going to use all that much of it. So just hold on and we'll see how this plays out, okay? All right, so the nature of chemical energy. The traditional way to measure work is below. Oftentimes, we don't have the ability to traditionally measure work this way, so we have to do it something a little bit different, okay? And so, first thing, work, W, is equal to work. And work is the energy transferred when a force exerted on an object causes a displacement of that object, usually measured in joules. Okay? Well, okay, so we're talking about work, we need to talk about a force. And so F is equal to force. Any push or pull exerted on that object, usually it's measured in newtons. There'll be some exceptions to that as we move forward, but for us, yeah, we'll get to that when we get to that. So, all right, hang on, close that. And the last thing that we need to do to talk about this is distance, D. And so distance is equal to D, and that is the distance that the object moves. Usually it's measured in meters. Okay, we bring these three things together, and the equation that I want you to think about is that W is equal to force times D. Okay, and the way that you can remember this, and the things that might make it a little bit easier for you, is this triangle over here on your left. Okay, and so a lot of times we can use triangles to help explain these formulas and know what we're getting into. And so the top of the triangle is going to be our force. No, top of the triangle is going to be our work. So we're going to put our W here, I'm going to put force here, and I'm going to put our distance here. Okay, so if I cover up work, and okay, I'm not covering it up because you can still see it, duh. But if I cover up the W, F times D is going to give me my W. Okay, if I cover up my F, W divided by D is going to be my force, and if I cover up D, the distance, work divided by force, is going to give me the distance. And so that's how you can use the triangle to make sure that you know what you're doing. Now, like I said, we're probably not going to use these a whole that often or that often much, but that's okay. So, all right, see you in a second. All right, drag the thing. Okay, so apparently I'm not actually live recording right now. Do I go here? What do I do? What do I do? Pause. There it goes. Okay. All right, so we're going to slide this up a little bit. All right, now, the energy that we see in chemistry classes basically is chemical changes is due mostly to the potential energy that the atoms have and the relationship that those two atoms have with one another. So the potential energy is due to the electrostatic, the opposite charges, the positive and the minus charges that those pieces have of the ions in the molecule. And we could find a good estimate of that energy through using something called Coulomb's law. C-O-U-L, Coulomb's law. Okay, and Coulomb's law is a fairly complex looking equation, but we're going to work through a little bit of it. And we're not actually going to use it that much, but just so that you're there, here we are. All right, so first thing we're going to look at is this variable. So E sub L. So this is the energy due to the electrostatic potential. Inside this formula, we're going to have Q1 and we're going to have Q2. So those are the two charges on the individual particles. We also are going to have D, which is the distance between those two particles. And so there's a constant that got thrown in just to make sure that this works all the time. That's a little k. It's a little k, not a big K. And this is a proportionality constant, which has a number of 8.99. Okay, I'll actually put it on the line in the right spot here. I'm sorry. So 8.99 times 10 to the ninth joules times meters divided by coulombs squared. And so when we're doing stuff like this, we usually use the charge on an electron in this equation, which is going to be this number, 1.60. 1.60 times 10 to the negative 19 coulombs of charge. Not a lot of charge on an electron. They're pretty small little beasts, and so they don't have a whole lot of charge in there. The distances are usually measured in nanometers, but first we got to convert those into meters. And so you got to pay attention to this one as well. You're going to end up using that conversion a fair bit. All right, so as we use this, oh, I'm sorry, we'll put that back where it goes here for a little bit. So the line is across my eyeballs for just a little longer. The equation is, here's what the equation looks like. So E sub EL is going to equal my proportionality constant. It's going to equal my little k times Q1 times Q2 divided by the distance between those pieces. Okay? And so that's the equation. We're going to use it a little bit, but we're not going to use it a whole bunch. So as it is, there it is, and we'll see what that looks like in just a second. So, all right, here we go. If you have any questions as you are watching this video, please notice on the bottom, I'm going to move up just a little bit so the lines are going to get in the weird spot, but you'll notice that I have the questions on the bottom for you, so feel free to write your questions in. We're going to have a lot of time in class to talk about all this stuff, and I want to make sure that you understand what's up. So I gave you a space to make sure that you could do that right here in the bottom of your notes, so please make sure that you do that. All right, here we go. Let's scroll this down. All right, now there's some pictures, so I'm going to stand over here and see what it looks like. Oh, look at that. Okay, so what I'm talking about here is Coulomb's law, and as we talk about Coulomb's law, what you're going to see, and let me just explain what's happening to one another here. So this is that energy of the system. Okay, this is the energy of electrostatic attraction, and it's going to be greater than 0. That's a positive charge. Okay, here's a negative energy. Okay, you'll notice that if we bring two charges together that have the same charge, you're going to see that it's an increase in the energy of the system. And so that's an increase in energy because it takes work to hold those two charges that are the same together. We can't, it's like opposite ends of a magnet. You got to actually hold them with your little fingers to make sure that they don't go anywhere. Okay? And so as that distance gets closer and closer, which is what this axis here, the dashed line shows us, here we're putting them closer and closer together, and it takes more and more energy to hold them there. Okay? And so we don't want that. Okay, now here, where we let those two positive charges come apart from one another, you'll notice that the energy level comes down, and the energy gets close back to 0 the further those particles get apart from one another. Okay, now, just like positive and positive charges, a positive and a negative charge, if they're further distance apart, they will have an energy between them that approximates to 0. It's asymptotic to 0, just like the other one is right here. But the more we bring those oppositely charges together, what happens is those pieces actually end up becoming attracted to one another, and then they glom onto one another. When they glom onto one another, what they're doing is they're actually releasing energy. And so a positive charge and a negative charge come together, and that releases energy. That decreases the overall energy of the system because we don't have to force those two pieces to be together. Those two pieces want to stay together because they're happy that way, and that just makes it easier for them. Okay? So there you go. That's what's going on in this one. Now, sorry. So let's look at this particular molecule now, okay? So if we look at a specific molecule, in this case we're going to look at table salt, which you guys know as well as I do, that is just NaCl. And so we see that the energy is released when we see that energy is released or is negative when those ions are close together. And so we already talked about this a little bit. We just talked about it, but I'm just talking about a specific ion here, all right? So if we look at this graphic, And you can't see my finger behind it, so I'll use the mouse pointer. Here we are, those charges are further apart and they're higher potential energy. But as we bring together, they have a lower potential energy, which means they're lower in energy, they release more energy to the area around them, and so that's a decrease in overall energy of the system because those particles can mash together and hold themselves together. So then on the flip side, if we were to separate those ions by pulling them apart, we would have to input energy to do that. Okay? And so we'd have to expend or input energy. So I'm going to write expend because I like that. It makes sense to me. So we would have to expend energy or input energy to do that. Now, this is going to lead us to two fundamental ideas that you need to commit to memory. So energy is released when chemical bonds are formed. Energy is absorbed. Whoa, I screwed that up. Energy is when chemical bonds scratch off bonds here, woo, are formed. Let's say broken. Okay, energy is released when bonds are formed. So, oops, typo. I gotta fix that. I'm sorry. Now, covalent patterns follow this as well. We're going to get to that in a little bit. So we're going to stop right here, and we'll come back to this one in just a second. Oh, I got to fix that. At this point, fucking go with it. Whatever, just leave it. Okay, so this is going to be we'll see. Okay. Oh, you're recording right now? How is that happening? That's funny.